Hey, everybody. So today we are doing part 1 of 2 of natural language processing. Today's NLP material is going to be what's in topic 39 that you see on Canvas. Tomorrow's session, I'm actually going to go through some of the appendix material just because I think it is very, very worth going through. It's just really interesting stuff that we'll see it tomorrow. So I'm not going to go into it right now. So in today's agenda, we're going to talk about what NLP is all about. One thing to note about NLP, and y'all will see this if you decide to do any NLP for this project or for the capstone, is unfortunately the processes are not super linear, or like it's not one direction. If you want to do EDA, you kind of have to do one method of pre-processing. If you want to do the modeling, it's another method of pre-processing, or not different methods, rather they undergo 2 different routes of cleaning or pre-processing. So we'll kind of see some of that today. So we'll talk about that pre-processing, and we'll talk about feature engineering as well. And at the very end of this notebook, we're going to go through a very, very quick example of text classification. And this is going to be on a satire data set, whether it's satirical or not. Something to talk about is the project for NLP. The NLP project is also classification. So I know both the image classification, which we're going to talk about neural networks next. Yeah, we're going to talk about neural networks next week. Both image classification as well as this project are both classification projects. So actually a lot of the same concepts from last project come through in these projects as well. So the metrics are exactly the same. The way you evaluate class imbalances, the only difference is the kind of data that you're feeding into your model. Other than like the pre-processing stages, the modeling is all the same. So yeah, let's get into it. So first, text analytics and natural language processing. So NLP, natural language processing, basically allows computers to interact with text data in a structured and sensible way. So in this section, we'll talk about some steps and approaches to common text data analytics procedures. And in other words, with NLP, computers are taught to understand human language, its meaning, and sentiments. So some of the applications of NLP are chatbots, and chatbots is actually something that is more of a neural network application. So when we talk about neural networks, I'll kind of talk briefly about how chatbots come into play. We can do classification of documents as well, speech recognition and audio processing. So speech recognition, because, we're not going to talk about the part where we process audio. However, once you have a transcription library or service that can turn your audio into words, you can pretty much do whatever you want with those words in these NLP ways. And audio processing similar to that as well. So audio processing, if there are words involved, some sort of transcription process, we can take the words, do NLP on it. I've gotten a few questions about dealing with audio data because, audio data is very interesting. Just as a quick note, we're not going to be covering processing of audio data in this course. However, two of the ways that you can process audio data such that it is relevant to the stuff that we're doing, 2 ways. One, if it's of like speeches or any spoken word thing, you can use NLP to process the text. Secondly, sometimes with audio files, if you can get like a waveform, you can actually do image processing on the waveform. So that would be really cool if that's something that you're interested in. All right, so let's take a look at the overview of the NLP process. I know I mentioned that it's not linear, or it's not like sequential in the way that your notebook will flow, but in terms of the process, it is. You'll see what I talk about when I talk about it later. So first, you have these raw documents, raw text. Next, you undergo this process known as tokenization. And we're actually going to talk about tokenization. It's basically the process of taking like sentences, paragraphs, books, articles. And the idea of tokenization is just separating them out into word by word. And we'll see some examples of that later as well. In pre-processing, we have text cleaning. So text cleaning is kind of different from data cleaning. We're going to see a couple examples of ways to get rid of noise, get rid of like outliers in your data. And that's in removing stop words and stemming and lemmatization. We'll talk about both of these later. And then the feature engineering is actually the part that takes your words and turns them into some numerical representation of those words. So we're going to talk about bag of words, TF-IDF, word embeddings. Word embeddings is what we're talking about tomorrow, actually. Then once your data is all in numerical form, it goes into your models, same way that we have done so as like the last phase, and then you can evaluate your models same way as we have already. So let's first talk about pre-processing, some of the libraries that we're going to be using. Within scikit-learn, we have a few text feature extraction text methods that we're going to be using. So here I mentioned something called TF-IDF. TF-IDF is one of these things. We'll see what that does later. There's also NLTK. NLTK stands for Natural Language Toolkit, and it is a Python library that just has a lot of language capabilities. Not only just methods, but also there are a lot of built-in corpora. Basically, like, think of it as it stores like a dictionary of words for whatever you want to do. So as an example, here you can actually download NLTK's bank of stop words if you ever wanted to filter out stop words, and we'll see what stop words are in a little bit. Punct is actually something for lemmatization, which we'll talk about later, and WordNet. If you ever wanted to only have like English words, for example, you can take a look at WordNet as well. All of these other things should look familiar. We have our scikit-learn machine learning processes. We have some plotting as well. And then we have our model over here that we're going to use at the very end. All right, so first, tokenization. Tokenization is usually the first step someone does in an NLP process, especially leading to EDA. So tokenization is the process of splitting documents into units of observation. So usually we represent the tokens as n-grams, where n represents the consecutive words occurring in a document. So in the case of unigrams, the sentence David works here can be tokenized into the 3 words David works in here. So it's not just n-grams, you can actually, sorry, not just unigrams, you can also have bigrams and trigrams and however many grams you want. So if you wanted to maybe use pairs of words as features, you would look at bigrams. If you want to do like 3-word features, you could look at trigrams. And I'll show you all a quicker way to do that later. But for example, this David works here can be tokenized into David works in here in the case of unigrams. And if you want to look at bigrams, we'll look at the bigrams David works and works here. So let's just say we have this review. Let me just make sure everything is run. So let's say we have this movie review. Let me run this review over here. This is the review that we've got. So there are many different kinds of tokenizers. If you actually take a look at NLTK's library, they actually have a bunch of tokenizers for different things. So the Regex tokenizer, and I'll explain Regex in a little bit. Regex tokenizer is usually the one that we use because it is the most, I guess, one of the simpler ones. Other tokenizers that exist, NLTK interestingly has a tweet tokenizer that can actually tokenize tweets in a specific way. So that specific one will clean out things like hashtags, mentions, any URLs. So that's really cool. If you ever wanted to keep phrases and sentences, there's also sentence tokenizer. So there's actually quite a few, but most of the time you can totally just use Regex tokenizer. So what is Regex? I know this is kind of a side, and I'm not going to go very much into Regex today. There are a couple lessons on Regex, I believe. But Regex is regular expressions. That's what Regex stands for. Regular expressions, R-E-G-E-X. And Regex is kind of like its own language to recognize patterns occurring in strings. So Regex is a language on its own. I am not a big fan of Regex because for me, well, not that I'm not a big fan. I always have to like kind of trial and error what works and what doesn't. This is a Regex. This is a regular expression. So this is an example of something written in Regex. It always starts with an R so that it knows it's a regular expression. And then this itself is the expression. And what this means is we're looking for any letters A through Z, any capital letters A through Z, and any digits. And this plus symbol just means it can be of any length from 1 to however long the word is. So what this means is it's going to recognize anything that matches this pattern as a token. Regex, I highly recommend if you're interested in NLP. There are a bunch of good Regex tutorials and also Regex games online that you can find. And yeah, if any of you are working on the NLP project, I'm happy to talk about Regex with you all. anyways, with this tokenizer, we've instantiated this regex tokenizer to look at these tokens or any token that matches this pattern. And basically, when you run the tokenizer, tokenizer.tokenize, it will turn it into a list of its tokens. Any questions about anything so far? All right. So the Regex tokenizer splits a string using a regular expression, which matches either tokens or separators within tokens. If you don't want to use a tokenizer, it is completely okay to just do a string.split. That, as you know, gives us the same result. So we do, I think it's review.split. It gives us pretty much the same result, except for we're not stripping any punctuation. So regex, you see, because any token or any element in this resulting list has to match this. Everything else we're actually going to strip out automatically using the regex tokenizer. If you're using just .split, just be aware you would have to clean out punctuation as well. So here you can see, where's an example? Oops. There is a full stop somewhere over here. Here, there's a full stop over here. So this is not cleaned out, which, as you'll see in a little bit, can prove to be, it just ends up being more noisy data. So highly recommend using this. Okay, cool. So from this review, you can see that we have 145 words. Awesome. So next, in terms of NLP EDA, some of the more basic EDA steps that you could do. First, look at the frequency distribution of your review. So freqdist, or frequency distribution, takes in a list of words and plots you word counts, basically. So if I run this, and this is an object as well, but you can kind of plot this too. You can see that this is the distribution of the words that we have. So if we zoom in, let's take a look at some of these words. The, to, he, of, movie, sure. I mean, we know it's a movie review. I is, so on and so forth. So just inspecting these words, and we know that this is a movie review, are these words very informative? And can we really extract useful information based on this frequency distribution of most common words? I understand that this is a subjective question, but just looking at these first few words, you don't really get much information. You don't really get much on like this, the context of what the review is talking about. Is the movie good? Bad? We don't know. We can't tell. What is the review referring to? Not clear yet, aside from like movie, which it's a movie review. Sure. So one thing that we like to do for NLP, and this is a way of denoising our data, is removing stop words. Now, stop words don't necessarily mean like they're outliers or they're not necessarily in the same category as noise. Stop words are just not useful in the context of NLP a lot of times. So one thing that we do to make our data a little bit cleaner is to remove stop words. So here we can grab our stop words. So stop words can come from different places, but one, we're going to download NLTK's version of stop words. So from here, you can see stop words, and you can actually look at English. I wonder if other languages work. We'll try this in a bit. And these are NLTK's default stop words in English. Out of curiosity, I've actually not done this. I just wonder if they're, oh, cool. Yeah, there's Spanish stop words as well. So for now, let's just have our stop words to be English stop words. And these are words that are just, what's the word? Semantically irrelevant or just not useful, doesn't help us gain information about the context of the text. So what we do once we have stop words, we can filter out our review. So this is one way to do it. And I'll show you all another way to do it for modeling later. But from here, if the word is not in a stop word, not in your stop words, we can just append that. And as you can see in this for loop, I'm doing one additional thing, and that is I'm turning everything into lowercase. And we'll see why this is important for later, but especially for modeling. But basically, since we're doing a frequency distribution, we don't want the capitalized version of a word and the word itself to be counted as two separate words. In some scenarios, you could argue that you do want to take that into context. But in this example, it doesn't matter if a word is capitalized or not. They have the same meaning for the most part. And so we're just going to turn everything into lowercase so that we have fewer unique words in total. So if we take a look at this, this is our filtered sentence. And we have basically cut our sentence down from 145 to 61 words. And if we take a look at this frequency distribution, hopefully it's a little bit more useful. You can see it's now movie, director, trying, say, story, beginning, portray something. Of course, this is a fairly short review. So you can see all the counts here are just one. So not, again, not the most informative, but in a larger context, maybe so. So the result of what we've just done in removing stop words is we have removed semantically meaningless words. All right. Again, I do want to highlight that the processes and the code that I'm using now is most appropriate for doing EDA. In a little bit, I'll show you all for modeling how it could be a little bit different. Okay, questions at this point before we move on to the next bit? Okay, so next we're going to talk about lexicon normalization. So aside from stop words, a different kind of noise can arise in NLP. So for example, the words collect, collection, collected, collecting, these are all similar words. So one way to reduce the number of features first and foremost, and also in reducing the noise or redundancy, because you can say that maybe collect and collected and collects are all kind of the same meaning. We can use stemming and lemmatization. You will choose one or the other, and I'll tell you right now that most people just do lemmatization, and you'll see why in a little bit. But first, let's talk about stemming, because stemming was what was done first. Basically, what they do is they reduce all variations of the same word to the root version of all its derivations. So first in stemming. So stemming allows us to remove the different variations of the same word. For example, collect, collection, and collecting will all be reduced to the word collect. So stemming is the process of reducing the inflection in words to their root forms, such as mapping a group of words to the same stem, even if the stem itself is not a valid word in the language. So stems are created by removing the suffixes or prefixes used with a word. So if we take all of these words, change, changing, changes, changed, changer, stemming will actually turn the word into change with no E. That's because it's just removing any sort of inflection to the word. And because this doesn't return you like a real word, that is why stemming is now not used as often anymore, but you can still use it 100%. But anyways, if you would like to do stemming, you get that out of nltk.stem, you can import what is called the Porter stemmer. There are actually different ways to stem, but Porter stemmer is the most popular one. Let's import that. You instantiate the stemmer, and then we loop through our filter review, and then we append Porter stemmer.stem word. So we're just stemming each word. Our review ends up to be 47 words, same length as before. And then when we take a look at our stemmed review, this is what we have. So now you can see the word movie has been reduced to just M-O-V-I with no E. I think this is tries. This is something. I want to say this is beginning, I believe. But basically, it reduces the inflections of the word. And what we end up here, if we look at the frequency distribution of the stemmed review, I want to say that the order changes. No, it's still movie and director, and movie at 5. Now you can see that movie is up at 6. So perhaps there was an instance of the word movie with a plural form that has been reduced to movie to match the singular form. So this is another way of reducing the noise in your data. Cool. So stemming is one way to reduce noise. Most people nowadays don't really use stemming anymore. Most people use lemmatization. So the only difference between lemmatization and stemming is that lemmatization returns real words. So instead of returning MOVI for movie, like Porter stemmer would, movie will be returned by lemmatizer. So again, it properly ensures that the root word belongs to the English language. And in lemmatization, the root word is called the lemma. So all of these words, same example that as we had for stemming, will all be reduced to the word change. So a lemma is the canonical form, dictionary form, or citation form of a set of words. So to do that, we have WordNet Lemmatizer, and that's actually why we had to download WordNet over here. This is something that you only have to do the first time you run NLTK, by the way, because this actually downloads into your local computer. But anyways, from lemmatization, we have instantiated our WordNet lemmatizer. Make sure that that is run. And then let's see some lemmatization in action. So once we run this, we can see that movie gets reduced to movie. Collecting gets reduced to collecting as well. So does collection, and collections gets reduced to collection. Now, why didn't collecting and collection get reduced into the word collect? Now, lemmatization usually ends up with more unique words versus stemming. So that might be one reason why you choose to use stemming over lemmatization, even though a real word is not returned. But basically, as long as a word exists in the dictionary as like its own entry in the dictionary, lemmatization will not reduce it any further. So it just helps to keep track of the fact that collection could mean a different thing from just collect, which is true, right? Like a collection of things is different from when you collect something. And I guess collecting, I don't know, are there different meanings of collecting? Probably, I don't know. But you'll see that's why this hasn't been reduced to collect. If you take a look at stemming the word movies and stemming the word collection, stemming turns it back into collect. And you can expect that when you use stemming, you end up with fewer unique words overall. Lemmatization, you have more unique words. Cool, so let's lemmatize our original reviews. We end up with words like this. Cool. At this point, any questions?
So does lemming also take into account like verb, adjective, noun as well, maybe? Or
I think so. Yeah, I believe
okay.
so. Yeah, and also good to know that like at this point, when you have your words in this form, this is when you do like your EDA graph. So you do your frequency distributions. I'm not sure if I have any here. I think I do. So I have like a word cloud. Do I have a word cloud? Let me see. Yeah, I have things like word clouds over here. You need words. You need your data to be in like the list of tokens format in order to do EDA like this. Cool. All right, so any questions before we talk about the next section? All right, so next, feature engineering. So feature engineering is really the part that turns your text data into some numerical representation that can be understood by our machine learning models. So this is really the part where you're turning the words into numbers. I like to call feature engineering or any of these processes that we're going to talk about vectorizing as a general umbrella term, because we're turning words into vector representations of themselves. So far, the ML algorithms that we've seen represent features as variables that take on different values for each observation. So for example, we will represent individuals with education levels, income, so on and so forth. So this is done slightly differently in NLP. In order to pass data to ML algorithms, we have to represent each text observation numerically and as a set of features. So one method, and that's the only method we're going to talk about today, is bag of words methods. So the two vectorization techniques we're going to talk about today are count vectorizing as well as TFIDF vectorizing. Now, both of these fall under bag of words methods. So a bag of words model, or BOW for short, is a way to extract features from text for use in modeling. A bag of words is a representation of text that describes the occurrence of words within a document. And basically it involves two things. One, a vocabulary of known words, and two, a measure of the presence of the known words. So it's called a bag of words because any information about the order or structure of words is not taken into account. The model is only concerned with whether words occur, not exactly where in the document it occurs. It will sort of see in the resulting data frame that you get why that is. So the intuition behind using bag of words is that a document is similar to another if they have similar contents, which makes sense. So bag of words data can be represented as a document term matrix or a term document matrix. It looks like this, in which each column is a unique word and each row is a document. For example, we have 4 documents over here, very, very simplistic. I love dogs, I love cats, I love all animals, and then I hate dogs. These 3 first documents can be represented this way. Each unique word becomes a column, and the values here will just be the word counts of each word occurring in each document. So you can see in document 1, that's I love dogs, love gets a 1, dog gets a 1, I gets a 1 as well. Everything else should actually be zeros, not blank. So everything else automatically will be encoded as zeros. And so because of this representation, but you can see that the order of the words does not get taken into account in this vectorization technique. So how do we do this in code? What we do is we import count vectorizer and count vectorizer, and this is where we kind of have to work backwards. After we do our EDA and we have our list of tokens, we kind of have to go backwards because count vectorizer for each document takes count vectorizer takes each document as an entire string. So earlier when we had documents split up into a bunch of tokens, we have to put those tokens back together for count vectorizer, unfortunately. So because of that, usually EDA is done in one process, modeling is done in another. So using count vectorizer, and we have these documents over here, this can be a list of documents. This can also be a column in your data frame. That will also work. And we'll actually see that later. So let's say we have these docs over here. I just have to instantiate count vectorizer and I do a fit transform, just like doing scaling in scikit-learn. So I do my fit transform on the docs. And by the way, if you're doing your train test split, you also fit transform on your train set, transform on your test set. So when you do that, and actually let me first show you, I stored this transform version to the variable X, and X looks like this. By default, count vectorizer outputs a sparse matrix. Now it's a sparse matrix because sparse matrices, or this sparse matrix data type is a lot more efficient in storing data versus a dense matrix, because usually if you have a lot of text, you actually end up with a lot of zeros in your data frame. So even here, like in these 4 short sentences, we have more zeros than ones. You can imagine with more unique words across more different instances of text, you'll get much more sparse matrices. I think most text data ends up with sparsity of like over 95%. And that's normal. So to put it into a data frame, we just have to do toArray. And then, as you can see here, we don't have any feature names, but the vectorizer has our feature names. So vec.getFeatureNames, get feature names gives us our feature names, and those actually correspond in the same order as the columns. Cool, actually I had that down here too. Let me quickly pull up our count vectorizer documentation, because I think there's some important things to talk about here, which I'll show you all later in a bit. So what we did here in the methods, we did our fit transform. So you can also do your transform, but you can also do your inverse transform, which is really cool. And we got our feature names from there too. Oh, it's deprecated. Anyways, it seems like you'll get your output feature names from here. But anyways, some important arguments to know about within count vectorizer. There are quite a few. So first, in your pre-processing, you can have a specific tokenizer over here. So if you want to use one of NLTK's different tokenizers, you can actually use them in place of the default here. So that goes there. You can actually give it your stop words as well. So because of that, a lot of people, when you're doing the modeling process, you actually go back to your form of data before cleaning and clean out your stop words through your vectorizer. So you can give it stop words here. Or if you just want to re-filter your data for stop words just in case, you can do that twice as well. Something else that is important is if you have a huge data set with a lot of unique words, you can also use max features. So max features is over here. Max features basically will only keep the number of unique words that you tell it to. So let's say in some data set, you have like 100,000 unique words, which is actually not uncommon, but you only care about the top 1,000 words. And this could be for several reasons. One, you don't want to have additional noise in your data. Let's say you are processing tweets and people don't tweet with like perfect grammar, perfect spelling. So you might have like instances of like, let's say like ha 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 with like 10 ha's versus like 9 ha's will each be individual words. And if that only occurs one time in your data set, it's going to make an entirely new feature for that single occurrence. So one, it is getting rid of noise. Two, it also will just help your models run faster, right? Because what's the point of including words that only occur like, let's say less than 5 times? So definitely I do recommend using max features to cut down the number of columns that you have in your resulting data frame. There are other ways that you can control this. So for example, there is min and max DF as well. So you can ignore terms that have, you can ignore terms that have a document frequency lower than a given threshold. So let's just say, yeah, this is kind of controlling it per document, whereas max features does it per corpus, and corpus refers to all the documents. Cool. Something else that's cool as well is n-gram range. So I didn't really talk about that in terms of looking at bigrams, trigrams. That's something we talked about at the very start. If you want, you can actually vectorize into bigrams too. So if you want to consider unigrams and bigrams, you would actually set this to be 1, 2. If you want to even look at trigrams, you can do 1, 3. However, once you introduce bigrams and trigrams, the number of features will explode. So because of that, don't forget to control your max features. I understand that this is a lot, but any questions at this moment? This count vectorizer, any sort of text vectorization does take a bit of getting used to. But any questions at this point? All right, so back to this. We're going to do an extremely simplistic example of text vectorization. So here, I'm just going to run, I'm just going to create a y, our target variable, for 0 to signify animal lovers, 1 to signify animal haters. So here I have my array of y values. If I fit my count vectorized data frame over here, I fit my df with my y, I can make predictions, and I so happen to return 0001. We'll see like an actual example towards the end of this notebook. Cool. So as an alternative to count vectorizer, another method of vectorization that also takes into account, oh, we'll see what it takes into account. It's called TFIDF, and TFIDF stands for term frequency inverse document frequency. That's what TFIDF stands for. So what does TFIDF do? It normalizes the raw count of the document term matrix, and it represents how important a word is in the given document. So term frequency is exactly what we did over here. Term frequency, word count, same thing, but it is doing it in inverse document frequency. So IDF, the TFIDF, IDF of TFIDF basically measures how much information a word provides, if a word is common or rare across all documents. And this is the formula for doing TFIDF. But basically, if a word is uniquely used in one document versus other documents, it will have a higher value. So let's just say your data is a bunch of, I don't know, your data is a bunch of articles about animals, and most of the articles are talking about cats and dogs, but you have like 2 articles that talk about like hamsters, for example. In those 2 articles that talk about hamsters, the word hamster will have a much higher TF-IDF value because it is more unique to the document itself. So that's what TF-IDF is a measure of. Anything to clarify about that? Cool. So basically what TF-IDF helps with is, let's say you have very commonly used words like the, or depending on the context, if you're doing like movie reviews and you have a word like movie that is used in every single review, it will be given a lower value because it's less important and less unique to the review itself. Okay, so let's just use these movie reviews as a quick example. Copy and pasted this from somewhere. And these are our reviews. Now, I can use the count vectorizer, which is this count vectorizer. We're doing our regex. We can, as you can see, we can have our tokenizer from NLTK in there. We can lowercase within count vectorizer. We can have our English stop words too, and we can fit transform. We already looked at that sparse matrix thing already. And then if we look at this, this is what our data frame looks like. So as you can see, I have now 4 longer reviews, but just like that, because there are 269 unique words, we have 269 columns, which is, I think, a lot more than what we've been dealing with so far. But anyways, using the TF-IDF vectorizer instead, here we go. You can see that we end up with more columns. Hold on, we have more columns because we are using different arguments. So let me quickly do this just to make sure that it is standardized. TF-IDF vectorizer over here. Cool. So here, now we have the same words, but now you can see that all of our numbers are normalized. So all the numbers are between 0 and 1. Mostly they're very, very small numbers, but the numbers will basically represent relative importance of a word. So when modeling using count vectorizer and TF-IDF, sometimes you can get different results. Cool. Any questions at this point? I know the concept of TF-IDF can be a little bit abstract to think about.
So just to kind of clarify, the higher the number, the more important it is, and the less documents it's found in?
Yes, yes, that's a good way of putting it. Exactly.
Okay, thank you.
Cool. Anything else? All right, so let's work through a text classification example. So let's do this example of a satire versus non-satire data set. So typically what we have is data that looks like this. We have our body of text as one column, and usually you don't see the entire text, which is fine, it's normal. And then you have your target column, exactly the same way that you would have for our numerical data. So taking a look at value counts, this is going to be a perfectly balanced data set. And then if you look at the head and the body, you can see that this is what one instance of text looks like. Cool. So first what we do is we're going to split up our X and Y because we're going to do a bunch of pre-processing on our text, and our Y pretty much will stay as is. It's okay to do this because the order of your text will be preserved. So pretty much when you put them back together in your modeling processes, you have nothing to worry about. Cool. All right, so first let's tokenize. And here you can see I'm using the dot split method of doing that. Just if you wanted to do that, if you don't care about the noise of punctuation, so on and so forth, you can totally do that as well. So this is that. And something that you can do, you can see that our total number of words, and here we're doing just lowercase of all of these. We have 41,000, over 41,000 words. Next, if we want to lemmatize everything, lemmatizing everything, you can see that our first text becomes a little bit more cleaned. So less looks like that's what happened. I wonder if there's anything. I guess there's nothing that's super obvious right now, but doesn't matter. This is all lemmatized. So now that we have our lemmatized output and our target, and this is the lemmatized output, which we don't really need to look at. Let's do some quick corpus statistics and EDA. So with the stop words, you can actually add to your stop words, and depending on the context, you can choose what stop words you want to add. And this is something that can be a back and forth process that you do in your EDA. So let's say in this example, when I was making my word clouds, I saw, or when I was doing like my frequency distribution, I saw these come up a lot. Satirewire.com, because that's where I got a lot of the text from. Satirewire kept coming out. I had the copyright symbol too. A lot of these random punctuations keep showing up because I didn't use the regex tokenizer. So you can pretty much always add to your stop word list based on your context. So let's say you're dealing with movie reviews, you can take out the word movie, you can take out the word watch, maybe, depending, up to you. So with this, you can see that our stop word set is a little bit longer now. So we have all of the words that we had before, but also we have things like the copyright sign that we added, satire wires in there now too. Whereas I think like HTTPS is usually in there somewhere. I don't know if I added that already, but you also have a bunch of punctuation as well. Cool. So with this, let's take a look at some word frequencies. First, I'm splitting up my data into satire and non-satire. And the reason I'm doing this is because, as you know, from the last project, since we're doing a classification task, our EDA, we're trying to do a comparative EDA as well. So we have our satire, non-satire. Cool. So let's split everything up, tokenize each of our satire and non-satire words. We can see that we have this number of unique words in our satire text, slightly fewer in our non-satire text. And for EDA, we're just going to flatten it all into a single list. Cool. Now with that, we can find out what our most common words are. We can do this like this, or we can look at normalized frequency. Actually, let me see if I have the bar graphs. Cool. All right. So normalized frequency is helpful because we can see, all right, out of all the words that we have, how many percent of the words are the? So here, 1% of all the words used are the word the, and so on and so forth. Cool. Now from here, just some quick visualization. There are many different ways that you can visualize this. You can use the line graphs like we had at the start of this notebook, but also you can use bar graphs. So in this example, oops, I'm going to run this. You can see that these are the distributions between satire and non-satire. So maybe you can start to look and see what are the main differences in the words that are being commonly used across both classes. So in satire, we can see that maybe it's a little bit more general. It could be dependent on the data source as well. It looks like this might be more European because there's EU in here. Teresa, I'm guessing for Theresa May in the UK. And in not satire, it's a little bit more US centric, right? At this point, this notebook was from a few years ago. We have the US, we have government, President Trump, police, House, so a little bit more US centric, which can probably uncover some potential biases in the data. But again, for comparative EDA purposes, you can look at it like this. Next, word clouds, which I scrolled through to a little bit earlier, but word clouds are a very visual way of looking at word frequencies. And based on this, I probably should take out the word the. And this is something that, again, you can go back and forth with, cleaning out stop words, cleaning out any words that are not meaningful in a sense. So something that I would like to point out as well is that if you would like to do word clouds, make sure in your notebooks to also include something that is a little bit more quantifiable. That's important because word clouds, you have, sure, the word the is very big, but you don't really have a measure of the actual counts. So usually word counts, I say that these are good for your non-technical presentation. And then for your bar graphs and all that, have them in your technical notebook when you're presenting your project. Cool. So the code for word clouds all there that you can use. Cool. So let's do a really quick full modeling process. So here you can see that I'm using XLem and YLem, which is what I got from like all the way back up here somewhere. Yeah, I gotten that for all the way from here. So as you can see, what I was talking about, like that it's not very linear, is that because EDA processes take your data one way, modeling take your data in a different way, you kind of have to like backtrack a little bit, but that's just how it is. So I'm taking my XLem and YLem. That's the data that was lemmatized and filtered. We're taking that, we're going to instantiate our TFIDF, this time with stop words from our stop word set that we uniquely defined earlier with the satire wire with the punctuation, and then transform our fit transform our train, transform our test. And as mentioned before, we get that sparse matrix. And as you can see here, this is the dimensions of our sparse matrix. So our train set had 800 rows and 21,000 unique words, or 21,000 columns. These matrices, again, as I was mentioning, are usually very sparse. Oops, let me run. Where did I run this? Sorry, give me a second to rerun what I need to rerun. There we go. Perfect. Cool. So average number of non-zero elements in vectorized articles. That means the average word length of each article, basically, that's 167. And the percentage of columns containing 0 is 99.2%. So that is how sparse the matrix is, because there are so many unique words, and I'm guessing a lot of words that only appear maybe once, twice, fewer than 5 times. That's why you have a lot of that sparsity, and that's what setting max features is useful for. Cool. So in instantiating the classifier itself, I'm going to use random forest first, although it has been shown that naive Bayes usually performs a lot more efficiently. I want to show you our random forest because of feature importances. Here I have random forest classifier over here. When you instantiate, it has nothing to do with the data that you're giving it, so you instantiate it in exactly the same way. You can also do your grid search in exactly the same way as well. Fit it and make your predictions on your train and test set. And pretty much you can use the same function that you use for your last project too, if you want. So that's cool. So here I have my classification report. You can see there's slight overfitting. I have my confusion matrices here as well. Cool. And you interpret these exactly the same way you would interpret your classification models from the last phase. So one thing that's cool about feature importances is now you can actually look at the importance of words. So here what I'm doing is I'm grabbing the feature importances from there, and I'm also grabbing the feature names from the vectorizer. You can also get it from your X train if you set it as your column names of your X train. So looking at this and I'm plotting my feature importances, now I can see that the words Monday or even or government are the most important features. And from here, I think it's not directly obvious which direction the words will bring a text to be classified. So the word Monday, is that more satirical or more like actual news? We don't know. And so going back to post-modeling EDA, which I definitely talked to all of you about your post-modeling EDA for your last project. This is something that you would do. And for words especially, this is why I briefly talked about normalized frequencies, especially if you have class imbalances. I can get into more of that detail at one-on-ones with projects or when we get to our projects. But basically what you will want to do is take a look at the words Monday or even, go up to your normalized frequencies and find out where the normalized frequency of those words, and whichever one is more, that means Monday is more important for a certain word versus for a certain class versus the other. Does that make sense? Anyone have any questions about that? Conceptually, same thing as what we're talking about with the last phase, just now instead of numerical features, we're actually talking about words as features. All right, cool. So we've gone through an entire process of NLP. NLP in itself is like its own big topic, in my opinion. So there's a lot to uncover, and the processes can be a little bit confusing, but my recommendation is take it slowly and try and figure out what you're doing at each step. So many NLP projects I've seen pretty much copy a lot of these cells and then just use them in the project, but a lot of these cells are not relevant for every project. So please, if you're using this code for an NLP project, look at what you're using and figure out whether it's actually useful or not. Cool. So preview for tomorrow, or conclusion first. Conclusions: learning foundations of NLP allows us to represent our language in a way that computers can understand. ML algorithms that we talked about in the last phase can be used to classify these text documents. However, there are still disadvantages to representing language this way. For example, we lose things like the order of your words being used. Because we normalize it so much, we sort of lose tone and we lose context. Like, for example, if someone's like angrily screaming at something, since we did all lowercase to clean our data, we lose that subtext or that subliminal meaning of the text or whatever that is. So tomorrow we're going to talk about other vectorization methods that help you to retain that information. So those will be really cool. And that is under word embeddings. And tomorrow I'm also going to talk about the clustering method that people typically use for NLP data or for natural language. So that is known as topic modeling. And that's something that we're going to talk about tomorrow as well. All right. my recommendation, if you want to work on NLP, is just to let all of this just slowly sink in. But at this point, any questions and anything I can clarify?
Quick question.
Mhm.
This is about the actually the phase 5 project.
Oh, yeah.
Do you want, because I was under the assumption, do you want us to pick a project that's similar to that or not similar to
Oh,
that?
like phase 4 versus phase 5?
Yeah.
Mhm. So it's really up to you. My recommendation is actually to do something that's different. So if you want to do
Okay.
NLP for phase 5, try to do something different for phase 4. And the reason for that is just so you have more variety on your resume.
Mhm.
Unless you really feel passionately about a specific, part of data science, like
Mhm.
if you really, really want to work with natural language processing, for example, then sure, you can do 2 NLP projects. However, when you're doing your capstone project, I will try and help you as best as I can to make the 2 NLP projects different enough.
Okay.
So you have more things to talk about in interviews.
Okay.
Yeah,
Okay,
but
that's
usually
all.
I recommend to do different things. Like for
Okay.
example, like I knew I really like recommendation engines. So I did the neural network project for my phase 4 and then
Okay.
reckoned as my capstone. And so I could talk about both things
Okay.
for my resume.
Okay.
Cool. Anything else? All right, really quickly, the data for this project, the NLP project, is classification on South by Southwest tweets. And this is for some reason South by Southwest in 2012. And this is when I think one of the first generations of iPad was coming out. Google Circles was a thing. So that's what the text classification on, and it's basically classifying whether the tweet was of a positive or negative sentiment. So sentiment analysis, which is actually one of the biggest applications of natural language processing. So that's what the project is. However, I will say that getting text data is a lot easier than getting numerical data because I don't know why. There's just a lot more text data available versus numerical data, and because you never have the issue of I need to have a certain number of features, because your features will always be enough because there's so many unique words being used. So if you want to use your own data for any of the projects, again, please just let me know beforehand. Cool. Any last thoughts, questions before we call it for the day and we continue this tomorrow? Cool. All right. Well, if there's nothing else, we have all this other stuff to talk about tomorrow. That's going to be really cool and exciting. To preface, some of this stuff will involve some neural network stuff, but next week we talk about neural networks, so it won't be too long before we're like, what are we doing here? So all right, if there's nothing else, I will talk to you all tomorrow. You guys have a good rest of your day, and yeah, let me know if you ever have any questions. Good night, you guys.
Thank you. Good night.
Bye.
Thank you.